Section 4.6, Dimension. In the previous section, we talked about bases, and we talked about how the standard basis for Rn has n vectors, so R3 would have a 3-vector basis, and so on. It kind of makes sense that all bases for a finite dimensional vector space would have the same number of vectors, which is the first theorem for this section. In addition, if V is an n-dimensional vector space, and V1 through Vn is any basis, then if a set in V has more than n vectors, it must be linearly dependent, and if a set in V has fewer than n vectors, then it wouldn't span V. Both of those statements should be kind of self-evident. If you don't have n vectors, then you can't make every vector in V, and if you have more than n vectors, then one of the vectors must be a linear combination of the other ones, if it's a basis. Next up, we'll define dimension. The dimension of a finite dimensional vector space V is denoted by dimension of V, and it is defined to be the number of vectors in a basis for V. In addition, the zero vector space is defined to have dimension 0. This is a good definition because we know that no matter what basis we look at, it'll have the same number of vectors by this theorem over here. Otherwise, this wouldn't be a very good definition because then the dimension could vary depending on the basis. As an example, how about we find the dimensions of Rn, Pn, and Mn? Well, for the dimension of Rn, we look at the number of vectors in a basis for Rn, and it should be n. For the dimension of Pn, well, remember that that's polynomials of degree n. So, for example, for first degree polynomials, let's say P1, a basis would have 1 and x in it, right? Because you have to be able to build all the constants of the degree 0, and you have to build all of the first degree polynomials, etc. So for P2, it would have an extra one, etc. So it looks like the number of vectors in each basis for Pn should be 1 more than n. If we look at the dimension of m by n matrices Mn, then that should just be the number of vectors in each basis over there, which should just be the number that you get when you multiply the two dimensions, right? If you've got, for example, the 2 by 2 matrices, then you have to build 4 different matrices, each one with 1 and a bunch of zeros in it, with the 1 in a different spot. So we just take the 2, multiply it by the 2, we get 4. So you could probably think that you could extend that in general. Just take m, multiply it by n, and that'll be the dimension. That'll be how many vectors are in a basis. If S equals V1 through VR is a set of linearly independent vectors, what is the dimension of the span of S? Well, we know that S is linearly independent, right? So that implies that S must be a basis for the span of S. Because S obviously spans the span of S. S is linearly independent. Great, so that means that the dimension of the span must be the number of vectors in the basis, which is just R, because there's R of these guys. Okay, how about we find a basis for and the dimension of the solution space of the homogeneous system given over here. Remember that we first looked at this in example 6 of section 1.2. When we solved this system, we saw that x1 could be written as minus 3r minus 4s minus 2t. x2 would equal r. x3 would equal minus 2s. x4 equals s, and x5 equals t, and x6 equals 0. So that was a solution. So what we could do is we could write out this entire thing as x1, x2, x3, x4, x5, x6 equals minus 3r minus 4s minus 2t, and then that's the first one, then it's r, then minus 2s, and then s, t, and 0. And if I want, I can rewrite this as a linear combination by pulling out the r's, s's, and t's. So I could write x1, x2, oops, I need a comma, x3, x4, x5, x6 equals r times, well, let's see, there's minus 3 over here, then there's 1 over here, and then there's 0 r's in the rest of them, so we just have minus 3, 1, 0, 0, 0, 0, plus s times, okay, well, there's minus 4 over here, then there's no s's over here, then there's minus 2, so we do 0 minus 2, and then there's 1s, and then the rest are zeros. And then we'll add that to t times, well, it's minus 2 t's in the first one, then there's no t's for the next 3, and then there's 1 t, and then the 0. Okay, so this I could write as minus 3, 1, 0, 0, 0, 0, right, 1, 2, 3, 4, 5, 6. So that would be this. Then I could write minus 4, 0, minus 2, 1, 0, 0, minus 2, 0, 0, 0, 1, 0, and I could set that as these 3 column vectors for these guys over here. I could set that equal to 0, 0, 0, 0. Well, 6 zeros, really. This row right over here tells us that, for example, r has to be 0, and this one says s has to be 0, and this one says t has to be 0 in order to be 0, 0, 0. Because remember, you could take 2 of this, add it to this, get all zeros over here. You could take multiples of these guys and get zeros on the top. So the solution over here is only when r, s, and t are 0. In other words, these column vectors are linearly independent. So that tells us that if I set v1 equal to minus 3, 1, 0, 0, 0, 0, v2 equal to minus 4, 0, minus 2, 1, 0, 0, v3 equal to minus 2, 0, 0, 0, 1, 0, that v1, v2, and v3 are linearly independent, because the only way that we can get 0 is trivially if r, s, and t are 0. So notice also that by choosing r, s, and t, we can build up any x1, x2, x3, x4, x5, x6 just by the nature of this equation right over here. That shows us that v1, v2, and v3 also span this homogeneous system, the solution space of this homogeneous system. So we found a basis, because v1, v2, and v3 span and are linearly independent. So that means that the number of vectors in any basis must be 3, because all bases have the same number of vectors by the first theorem we talked about in this section. So that means that the solution space has dimension 3, because remember, the dimension is just the number of vectors in any basis. And there's 3 vectors over here. Next up, we have the plus-minus theorem. If S is a non-empty set of vectors in a vector space V, then if S is a linearly independent set, and if V is a vector in V that is outside of the span of S, then the set S union V, that results by inserting V into S, is still linearly independent. If V is a vector in S that is expressible as a linear combination of other vectors in S, and if S minus V denotes the set obtained by removing V from S, then S and S minus V span the same space. That is, the span of S is equal to the span of S minus V. So what we're saying is, if we have a linearly independent set, and we have a vector that is not in the span of S, then the new set that we get will still end up linearly independent, because it wasn't something that could be expressed, I guess, as a linear combination of the other ones. It kind of makes sense. If it's not in the span, it can't be a linear combination, so just throwing it in there just makes us a bigger linearly independent set. But also, it makes sense that if we have a set that's expressible as linear combinations of the other vectors, and we remove that vector that's expressed as a linear combination, it's almost like it's redundant. So it makes sense that the span should be the same. It shouldn't be affected by removing it. Okay, how about we show that these 3 polynomials over here are linearly independent? Well, notice if we take the set S equals P1, P2 of just the first 2, so that's 1 minus x squared and 2 minus x squared. I could multiply this by 2, but then there would have to be a 2 over here, so it should be kind of easy to convince yourselves that these guys are linearly independent. So this is linearly independent. So that means, well, look at P3. There's no way it's a linear combination of P1 and P2. So P3 is not a linear combination of vectors in S, and that tells us by the plus-minus theorem that if we take S and we just throw in P3, I'll write union P3 to indicate that we're just throwing in P3 and we're just throwing it in over there, then that'll equal P1, P2, P3, and that must be linearly independent by the plus-minus theorem. Shouldn't be surprising at all, because there's clearly no way that you could build this from these 2 guys, so it should make sense you couldn't build this from this, or really any combination of them. Next up, let V be an n-dimensional vector space, and let S be a set in V with exactly n vectors. Then S is a basis for V if and only if S spans V, or S is linearly independent. So we have an n-dimensional vector space, and we have a set with exactly n vectors. So all we need to show that's a basis is to show that it either spans or is linearly independent. Either one will do. So how about we prove this? How about we assume that S has exactly n vectors and it spans V? Let's prove it's a basis just by knowing that it spans it. Well, we have to show it's linearly independent. We have to show that the spanning V and the fact that it has n vectors forces it to be linearly independent. Okay, so assume it's not true that it's linearly independent. So first we'll suppose it's not linearly independent. Then some vector V in S must be a linear combination of the remaining vectors. So let's remove it from S. We'll move that vector from S. So then it follows that the remaining set of n minus 1 vectors must still span V by the plus-minus theorem, because that vector that we removed was supposedly redundant. But this is impossible since no set with fewer than n vectors can span an n-dimensional vector space. There's no way an n-1 set of vectors could span V. So it must be that our assumption was false. It must be that S actually was linearly independent. So that means that we know that it spanned because we assumed that. We know it had n vectors, but now we also know it's linearly independent, so it must be a basis. Okay, next up, how about we assume that S has exactly n vectors and it's linearly independent? Let's show that we get the fact that it's spanning for free. To prove its basis, we have to show it spans, so let's again assume that it doesn't span, and we'll show that's impossible. Okay, if it doesn't span, then there must be some vector v in V that is not in the span of S. Let's insert the vector into S. So then we have a set of n plus 1 vectors that is still linearly independent by the plus-minus theorem. But that's impossible, since no set with more than n vectors in an n-dimensional vector space can be linearly independent. One of them would have to be a linear combination of the other ones. So our assumption must be false, and therefore S must span V. Okay, so that's kind of cool. So that means that anytime we have a set, and we know that we already know that the vector space is n-dimensional, so we have to be given the dimension. We have to be given that the set has n vectors. If we know it spans it, then we automatically know it's a basis. If we know that it's linearly independent, then we automatically know it's a basis. We don't have to check both anymore. Okay, so how about let's explain why the vectors v1 and v2 form a basis for R2. Okay, well, notice if I were to try to multiply -3 to get 5, now there's no way that I'm going to be able to multiply that same number to get 5 for 7. So pretty clear that neither vector is a scalar multiple of the other. Okay, so that's the same thing as saying that this set is linearly independent. But I already know that R2 is two-dimensional, and I have a set of 2 vectors, and it's linearly independent. Okay, so I don't even have to check that it spans. It's automatically a basis now by the theorem that we just proved. Theorem 4.6.4. Okay, how about we now explain why the vectors v1, v2, and v3 form a basis for R3 in part B. Well, notice v1 and v2, if I were to take 2 times this to get the 4, there's no way that that would be 7. Should be pretty easy to convince yourself that v1 and v2 are linearly independent. In the xz plane, notice v3 doesn't have a 0 in the middle, so v3 is outside the xz plane. Okay, so that means that it's not a linear combination of the other ones. I can just throw it in, and I must have a linearly independent set by the plus-minus theorem. So again, we have a linearly independent set of 3 vectors. We know R3 is 3-dimensional already, so that means that this is a basis by the same theorem, 4.6.4. Last but not least, let's talk about these couple theorems. Let S be a finite set of vectors in a finite dimensional vector space V. If S spans V but is not a basis for V, then S can be reduced to a basis for V by removing appropriate vectors from S. If S is a linearly independent set that is not already a basis for V, then S can be enlarged to a basis for V by inserting appropriate vectors into S. So if we have a set that spans, it's not a basis, we just have to take away some vectors to make them linearly independent. If we have a set that's linearly independent, but it's not a basis, that just means it doesn't span yet. So how about we just add some vectors, and that way it'll span. Okay, so that should make sense. Next up, if W is a subspace of a finite dimensional vector space V, then W is finite dimensional too. Dimensional W is less than or equal to dimension of V, and W equals V. They're the same vector space if and only if they have the same dimension. So that's actually kind of cool, because that means that if we have a subspace of a vector space that has the same dimension, then it has to be equal to the original space. Okay, let's prove this. Since V is finite dimensional, there exists a finite set S spanning V. Since W is a subspace, W is a subset of V, so therefore this finite set also spans W, so that means that W is finite dimensional. So it's easy to prove A. For part B, part A shows that W is finite dimensional, so we're going to use that. So that means it has some basis S with W1 through Wm as its vectors. Either S is also a basis for V or it is not. If it's a basis for V, then the dimension of V is equal to M, so they have the same dimension. So that's where this equal comes in. If not, then because S is a linearly independent set, we can enlarge it, by the previous theorem, to a basis for V. This implies that, in that case, the dimension of W would have to be less than the dimension of V. So that means that the dimension of W is always going to be less than or equal to the dimension of V. Last but not least, how about we assume that the dimension of W is equal to the dimension of V, and that S equals W1 through Wm as a basis for W. If S is not also a basis for V, then being linearly independent, S can be extended to a basis for V. But this would mean that the dimension of V would have to be bigger than the dimension of W, which just contradicts our hypothesis. So that means that S must also be a basis for V, which means that W would have to equal V. And then the converse should be fairly obvious. If W equals V, obviously they have the same dimension.